Okay, so what I want to look at in this lesson is how scientists use um, spectroscopic techniques to study stars, and like how light can be actually studied and analyzed and used to determine different things about stars. So things like, what are the stars made of, um, what temperature are the stars burning at, for example. They can also look at things like their motion as well. And what I want to try and put across is how light and the properties that we've looked at in relation to light and this property of where light can be absorbed and emitted, how these properties can be used in order to actually study light, for example, that's given off by stars, and help us to be able to understand stars a little bit better. So one of the things I just want to kind of rehash as well, just to kind of get the point across. So if we have a look here, if we were to take white light, now if we take white light, if you were to take white light and look at this light that's traveling from this source, for example, in this case a bulb, um, and you were to go in and look at this line here, so remember light travels in a straight line, and you were to look at all the different wavelengths that are present within this light, what you will see is that it will actually contain all the light on the visible spectrum. So a way to think about this, if we have a look here, so this is the visible spectrum. So we can see here, so these are like similar when you look at a rainbow, for example, or sometimes when you look at when light passes through glass, it kind of splits it up into this kind of color. Sometimes you see it as well in puddles of water where oil has got into the water as well. You can kind of see these, you know, all of these wavelengths of color. Now, what you can say is that with each of these different bands of color, like the whole way across, literally each of these bands are associated with a wavelength. So remember, a way that we can think about it is that light travels as a wave, something like this. And let's say from one crest to the other, if you were to measure that, it will have a length associated with it. And each of those lengths then is associated with a particular color that you see here on this, what's called a continuous spectrum. So within white light, all of the wavelengths or all of the colors of light are present within the light that's given off by white light. If you pass this through a prism, then what happens is, depending on this length or wavelength of light, what will happen is, so if this is your prism, what's going to happen is the light will be bent at different angles. And then each of these wavelengths of light shows up as a line, let's say, on your spectrum. So if you have a look at this, there are lots and lots of individual wavelengths of light that are actually being represented here on this, what's known as a continuous spectrum. It's called continuous because it goes all the way from the reds all the way to the blues, and it contains all the wavelengths and colors of light from the visible spectrum. Remember, light as well is what's known as electromagnetic radiation. It's part of a continuum. So on one extreme you have, for example, radio waves, which are quite long and spread out. They have wavelengths. We don't detect radio waves as light, but we can use radios and antennae and things like that to turn it into sound and use it to transport information like sound, or like sound that comes out of radio, for example. Then on the other far end, you have, like, let's say, gamma radiation, which wavelengths would be very, very kind of tightly packed together like that. The wavelengths would be very small, and they carry an awful lot of energy. So that would be up this side of the spectrum. And as you move down this side, you're getting longer and longer wavelengths as well. Now, just to remember then, so that's your continuous spectrum. That's what happens. Now, if you were to take a gas, for example, so if you take a gas, let's say if you have, so you have the atom hydrogen, H2, and you turn that into a gas, like we see here. And then if you were to heat that gas, So you can add heat, or another way to think about it is if you put heat into it. So you can, for example, put this gas into a discharge tube and put electricity through it, or you can heat it up. What's going to happen is that gas, the atoms in the gas, the electrons, so imagine, so this is just one atom, this is the nucleus, here you have an electron. What will happen is when you add in energy, this electron moves up into this higher energy level, stays up there for a while, and then comes back down, and it gives off energy, or it gives off a particular wavelength of light. And that's what we, and then that when, if you take then, so imagine this is a whole gas cloud, and it's all being energized, if you like. The electrons are getting excited, it's giving off this radiation, and this radiation goes through a prism and then it's split up. Now, atoms such as hydrogen will give off very specific colors of light that we can spread out onto a spectrum like this. And those colors of light will be directly kind of associated with the way the electrons are arranged, let's say, within the atom of hydrogen. And it'll give you this unique, what's known as an emission spectrum. It's called an emission spectrum because what's happening is the atoms that are within your gas cloud, they're getting excited and they're emitting very specific wavelengths of light that are very unique to whatever elements make up that gas. And then these pass through a prism, they're split up, and we can identify them then as very specific bands that's on a spectrum. So if you compare it to a continuous spectrum, has all of the different colors of light, whereas specific elements, when they're heated into a gas, their atoms will give off just individual wavelengths of light associated with the electronic structure of that particular atom. Now, the opposite then happens as well. Like, not only will these atoms, so for example, will they give off or emit light, they will also only, remember, in order to get this, if you want to get this atom to move from this energy level to this energy level, an amount of energy that's equal to the difference between these two levels has to be provided to the atom. And that's a very exact number. It's very unique, and it's what's known as the quantization factor in relation to electrons. So again, the very specific amount of energy that's needed can be directly linked to a very specific wavelength of light as well. So another way of thinking about it is that, so if you actually take, let's say, this white light, and the light from the white light that contains all of these different wavelengths of light, if you pass that through a gas, so for example, like a gas of hydrogen, and then you pass that through a prism, what will happen is the bands that hydrogen, for example, will emit when the atoms are excited, those same atoms are going to, electrons are going to absorb these very specific wavelengths of light. They'll take them out of the white light. And so remember, like, this light coming in has to be an exact amount. So you can imagine if this light that's coming from white light, okay, it has these very particular wavelengths associated with it. What's going to happen is this gas cloud, when the light passes through it, it's going to take out or absorb these particular bands or wavelengths of light. And then when you pass that light and split it up on a spectrum like this, pass it through a prism, what you're going to do is you're going to get this kind of a setup here, which is known as an absorption spectrum. So it's basically, it's just like a continuous spectrum, except you have the wavelengths of light associated with the individual atoms taken out of it. So these are it's just a kind of just a quick review of what we're talking about when we talk about emission and absorption spectra. So then what we want to think about then is, so this is brilliant. All of this happens. We understand the electrons. We understand that light can be split up and it can be cast on a spectrum like this. And we can link in, for example, these emission spectra, we can link them back to specific atoms. And we can identify specific atoms. So how is that useful to us? Well, what we can actually start to do then is, if we take light that comes from stars, for example, and the sun being one particular type of star. And we pass that light. So imagine this hot gas here is representative of a star that's in the night sky. So that light that sunlight that's coming from the star, if you pass it through a prism, what will happen is it'll split up into these individual wavelengths. And then what you can do is you can do some really interesting things, because then you can start to look at, well, what type of atoms are within these stars that are giving off this particular light that we can look at and analyze. And we can use this then, so remember, each emission spectrum is like a fingerprint for a particular element. But what we can do then is we can start to identify the elements that are present within stars by looking at the spectra that starlight produces when we pass it through a prism. So what we can then start to do is we can start to use these spectra in order to identify chemical makeup. So if we have a look here, so what we're looking at here then are the spectra for three different elements. So we've hydrogen, and here, so this is hydrogen, this then here is calcium, and then this element here is mercury. Now what we can see here, so these are what are known as emission spectra. So basically, remember, if we have, let's say if we have a gas cloud of hydrogen, and this cloud is heated up, it's going to give off light, pass that through a prism, then we get this very unique spectra. So we have here an emission spectra for hydrogen. So we can see this is what it looks like. If we compare this to an emission spectrum for calcium, for example, we can see that they're very different. Okay, they have some similar bands of light that they give off, but on a whole they have different, their complete makeup is completely different. And then if we look at mercury then as well, so imagine if we're to be able to get the electrons in mercury atoms to become excited, what's going to happen is they're going to give off these very specific wavelengths of light. And these numbers down here represent the measurement or the wavelength of light. So imagine this is your light, and you have this length from crest to crest, which is known as the wavelength. Then that's what each of these numbers represent. So as you can see here, so the wavelength is smaller on the left hand side, and the wavelength gets wider and wider and wider as we pass across. Another way to think about it is the wavelengths that are closest together, like when wavelengths are closer together, they have more energy and they get bent more, let's say, when they pass through a prism. But we can clearly see here, like if somebody was to give you the emission spectra for hydrogen, you can see, okay, the gas that's given off, that's creating this emission spectra, must contain hydrogen. The gas that's given off this emission spectra must contain calcium, and the gas that's given off this emission spectra must contain mercury. So we can actually use it then, we can use this as a fingerprint to ID the chemical makeup of a particular gas cloud or a particular gas. So we can use it to look at chemical composition. So what we can actually do then, if we have a look here, so this here is the sun spectra. So basically, imagine you have the sun and you have light coming from the sun. It's going through a prism and it's being split up into all of its different wavelengths. So you can see here that, and this will be an absorption spectrum. So what's happening is you're getting white light from the core of the sun that's passing through, and it passes through an atmosphere that's around the sun. And then if we look at it then and we break it down through a prism, we get this kind of characteristic, what's known as an absorption spectrum. So you can see it's a continual line spectrum, but it has these very, very, like you can see them, very unique bands or wavelengths of light that have been taken out of the continuous spectrum. And this is light coming directly from the sun. So a way to kind of think about that then is, if we have a look then at the sun, so if we have a look at the makeup of a sun, okay, so in this diagram here, so you have the core, Okay, and then within the core, then you have liquid hydrogen. And hydrogen, what's happening is the hydrogen is being crushed together under massive pressure, and it's producing helium. And it's basically liquid metallic hydrogen and helium. So you have this fusion that's happening, and what's happening is that's generating huge amounts of energy. And then if we have a look here, so you have the core, which is extremely hot. As you can see here, these are the temperatures you're talking about. So remember, 100 degrees is like a boiling kettle if we look at the temperature in comparison to that. And what happens then is, if you look at these different layers that you have, so you have this layer here, which is known as the photosphere, and then outside that, then you have the chromosphere. So imagine then you have this white light, that's coming from here, and it's passing through this, let's say, photosphere here, and that's just like the setup that we have here. So imagine this is the core of the sun. You have the light coming through, and what's happening is it's passing through this, what's known as the photosphere. It's like a gas atmosphere that's around the sun. It's very close to the sun, but it's around the sun. And then what's happening is that light then is going through the depths of space, reaching Earth, and then what we do then is just like here, we pass that light through a prism and we create what's known as an absorption spectrum, and we look at this absorption spectrum. Now what we notice is that this white light, or light that's coming from the core of the sun, it's being passed through this outer atmosphere of the sun. So what we can do then is we can see when we look, for example, here at the absorption spectrum that's created. So remember, this is your absorption spectrum process. We can see these clear lines that are being absorbed. And these clear lines that are being absorbed here, these wavelengths of light, they directly relate to particular elements that must be present within this atmosphere, or what's known as the photosphere of the sun. So remember that particular atoms, when they will give off particular wavelengths of light, but they will also absorb those same wavelengths of light as well. So what we can do then is we can look at these lines here, for example, and try and match these lines up with particular emission spectra for particular elements. And in doing that, what we can actually do then is we can start to identify some of the elements that are present within the sun. So if we take this absorption spectrum that's been created by the sun, for example, all of this setup here, it isn't just being created by one particular element. It's being created by a number of different elements that are within the photosphere, or the outside atmosphere of the sun. So if we have a look, like what we can do is, so if we have a look, see this line here at G, so that line there at G, this line at F, and then if we look at this line down here at C, so we can see these very distinct bands that have been taken out or absorbed. What we can do then is we can actually match these up with the emission spectrum for hydrogen. So we can see that these individual lines here that we see in this absorption spectrum from the sun, they match up with the lines from the emission spectrum for hydrogen, for example. So we can see that these match up very nicely, and what we can then conclude then is that the sun, for example, it must contain elemental hydrogen within it, and it does. We know that we looked at the chemical makeup, it contains hydrogen within it. So again, like we can look at this and we can use this then to identify one of the particular elements that are present within the sun by looking at this spectra. Also as well then, if we have a look at, so if we see this line here at D here, so this line, or this absorption, is related to helium. So helium. So this line here, this particular wavelength of light is absorbed by helium as well. So what that shows us again is that we have hydrogen, and we also have helium. So the process, like how the sun generates its heat, basically what you have is you have hydrogen being crushed, hydrogen atoms being crushed together and creating helium. So that's not surprising that we actually see this element present, let's say, within the spectrum of light from that we look at and analyze from the sun. And also then as well, within this spectra as well, these lines over here at K and H, for example, they are associated with calcium, Ca2++ ions being generated as well. So again, this is just like very briefly kind of looking at how we can use spectra to look at to analyze stars like the sun, and we can start to look at and determine their chemical makeup. Now, what we can also use the wavelengths of light that's been emitted by stars to tell us about, we can use it to determine what's known as the temperature. So we can actually start to work out, we can start to analyze the light that's coming from stars, and we can start to determine, for example, the temperature of the stars. Now, what we're looking at here, this is what's known as a Blackbody spectrum. So basically, if we have a look here, so we can see here that we have, so basically along the bottom, it tells us the wavelength of light. So you can see here, we're moving from left to right across the spectrum. And from, let's say, from top to bottom here, it basically tells us the amount of light, or of those particular wavelengths of light that are being generated or given off by a particular star. So what we're doing is we're capturing the light from the star, and we're seeing like what wavelengths of light are being emitted by the particular star. So what we can see here is that we have a particular, so we have infrared radiation being generated off. So we can see that we have a certain amount of it being generated, different wavelengths of infrared light being given off, and then we can see like there's varying amounts of it. And then what we can see here is this is the visible spectrum, and we can see here that there's a particular wavelength that has a maximum amount of, or a particular wavelength, or an amount or a wavelength of light that is being given off by that particular star. Now what we can do then is we can link that wavelength of light that's been, the amount of it that's being generated by the star, with its temperature. So what we can do then is we can look at, so if we have a look here, we can see that roughly the green and yellow wavelength of light is being given off by this particular star with the greatest intensity. So what we can do then is we can look at this wavelength of light that's been given off, or has the most intensity, that's been given off with the most intensity, and we can start to use that to determine the temperature of the particular star that we're looking at. So what we can do then is we can use this law that's called Wien's law, and basically what it says, what Wien's law says, is that the temperature, just represented by a T, is equal to, it's a particular constant, so it's 0.00289 divided by the wavelength, and this is like what we're talking about then is the wavelength, the maximum, whichever wavelength has been given off with the maximum intensity. So this is like a formula that we can use that links in the temperature with the particular wavelength of light that's being generated or given off by a star, for example. So what we can do then is, with this link between temperature and wavelength that's being given off, we can look at what are known, this graph, for example, what's known as a Blackbody spectrum, and we can then determine the different types of stars based on the type of light that are given off, their maximum, which is at its maximum point, and we can have a look, and we can kind of look at something like this. So what we have here is, so if we have a look at this bottom wavelength of light, so this particular star here, so this line, it's given off a wavelength that's roughly in around this region, and then using this formula, what we can do is we can come up with the temperature. So we can see that this wavelength of light, or this maximum wavelength of light that's given off, can be tied in with a temperature, and this wavelength, for example, will give us this particular temperature. This wavelength will give us this temperature, this wavelength will give us this temperature, and this wavelength will give us this temperature as well. So what we can see here is that so imagine this is our wavelength. So this here is the wavelength. This is the light that's been given off. As this wavelength decreases, as it gets smaller, what happens is the temperature, the energy being given off, or the temperature, increases as well. So as this bottom number gets smaller, this number here gets bigger. And we can use this then we can use, by looking at these what are known as blackbody spectrums, or ultimately by looking at the light that particular stars are giving off, we can figure out the temperature of those stars, like so. We can link them in with a temperature like so using this formula. So what we can see then is that this process here of determining the temperature of stars by the light that's given off, we can actually then start to classify stars and put them into these particular types of groups based on the light that they give off, which indicates the temperature that they must be burning at. So for example, we have these different, so we have O class stars, and their temperature, as you can see here, they're very, very hot. And as you move down, so you have O, B, A, F, G, K, and M, the temperature starts to decrease as well. And this also as well, you can kind of think about this in relation to the type of light that they're given off as well. So they can be classified based on temperature and based on light, just like what we see here. So we have O stars, B stars, A, F, G, K, and M stars. So they're kind of just a way that stars can be kind of classified and broken up into groups, dependent on the type of light, that the wavelengths of light that they give out, and the temperature then can be linked in with those individual wavelengths using this formula that we've looked at here. So ways to think about, like these blue stars, for example, up here are relatively hot in comparison to these red stars down here, which are relatively cooler than the blue stars. And this is really useful then as well, because what we can start to do then is not only can we look at like the light that's the maximum wavelength of light that's given off and link that in with temperature, but then what we can actually start to do is we can take, like for example, a blue star like this, and we can actually start to look at its individual spectra, or we can look at any of these other stars, and we can start to look at their spectra in a little bit more detail in order to try and figure out the chemical composition of these individual stars. And this is what it looks like here. So what we're looking at here then we're looking at absorption spectra for these different types of stars. So for example, you have, like for example, O stars, you have B stars, and then you can see then within these you have like subgroups of B stars as well. So if we were to then, like, let's say, just focus on one of these particular stars, so let's say for example these white stars, which burn at this roughly around this temperature, and we start to look at the absorption spectra, what we can actually start to do is we can start to figure out what type of elements are present within this particular class of stars. So if we have a look then at these guys here, what we kind of can start to notice then is that we have some very similar lines, for example. So we can see here that this line here, so this absorption line, this line here, and then this line over here, these lines are related to hydrogen. So they're related to hydrogen being present. So we can see here that there's clear lines of hydrogen, that absorption lines, or lines. So for example, hydrogen will absorb these particular wavelengths of light if it's present. So we see that these wavelengths of light must be present, or these particular hydrogen must be present within these A-class stars, because we can see there's evidence of the absorption spectra of hydrogen present when we look at its overall absorption spectra. So what we can also start to kind of see then is as you start to move, so let's say as you move down the class of stars, so as you move down this group, what's happening is the temperature is dropping. So you can see as you go from O class stars all the way down to these M class stars, the temperature is actually starting to drop. And the lower the temperature is, the more there's not as much energy, let's say, within the stars. So therefore, more different types of atoms can start to form. The subatomic particles can actually start to come together because there isn't so much energy there, keeping them apart. So what you can see then is as you start, so let's say if you take these O class stars, for example, and A class stars. So O class stars are very, very hot, and there's very weak lines for example, for hydrogen that are present. The lines in the A class stars for hydrogen, for example, are much stronger because the temperature is just that little bit lower, and it allows hydrogen to actually start to form. But what we notice that over here on the very far left hand side, as you start to move down, these lines that are on the left hand side, these absorption lines that are present, and they're related to, for example, the formation of calcium. So what you can actually see then is that as the stars become cooler and cooler and cooler, these more complicated atoms are starting to be formed, like calcium, for example. And you can see then that that there's still some hydrogen present, but it's not as much as are present, let's say, up here within these hotter stars. So what starts to happen, and as the star starts to cool down, it allows for more complicated elements to be formed because there's not as much energy in there keeping the elements apart. And what will actually start to happen is you'll start to get simple compounds starting to be formed. So if you have a look down here at these M class stars, for example, you're starting to see titanium oxide, for example, here. And you're starting to see these other different, you have a lot more wavelengths of light being absorbed out, and as a result of that, what does that mean? It means that you have more complicated compounds being formed, like titanium oxide, and those more complicated compounds are absorbing, for example, absorbing more of the wavelengths of light that's being generated and passing through it. So what you can see then is as the stars, and this you can also kind of use this then to look at the lifespan of a star. As the star starts to cool down, you get more elements being formed, and these elements then start to form compounds then as well. And these all show up on the light, on the spectra that are being generated by these particular stars. So we can tell an awful lot. We can take the light from starlight and we can analyze it by using spectrophotometry, and we can tell all of this information by just looking at the light and analyzing the light from stars. Now, also as well, what we can do is we can kind of look at properties such as density as well by looking at these spectra that are generated by stars. So if we take, so for example, we have a white dwarf here. So we have a lot of matter that's very, very densely packed, and the light is passing through the photosphere of these very densely packed white dwarfs. And as a result of that, that's impacting the lines, the absorption lines that are being generated, as you can see here. They kind of come out kind of fuzzy and kind of spread out like that. And as a result, and that's a result of the light, having to pass through a very densely packed photosphere. And what happens is, like you get, so for example, a white dwarf has similar elements that make it up in comparison to a blue giant, but the difference is that the photosphere in a white dwarf is very, very dense and tightly packed. And what happens is you get this kind of a spectra being produced. Whereas on the other hand, with a blue giant, what happens is the light, so for example, the photosphere, the light that has to pass through the photosphere in a blue giant is much less, it's not as dense. And what happens is then it gives this kind of effect where you have much sharper lines being generated on an absorption spectra like this. So a way to kind of think about when it's densely packed like this, there's much more collisions. The light is being just absorbed a bit more by more different, slightly different wavelengths of light are being absorbed an awful lot more because it's so densely packed. The light is passing through a very, very densely packed space, which is the photosphere in a white dwarf, whereas in a blue giant, that photosphere is much more spread out, and as a result of that, you get these much crisper, cleaner lines being formed. So another way to think about it too is that the position of the lines, for example, where the lines are positioned on this spectra tells us, let's say, the composition or what the particular star is made up of. The lines that are being absorbed the most, okay, are the wavelengths that can indicate and tell us the temperature. And then like this fuzziness of the lines, for example, can give us an indication of the density in relation to the star as well. So what we can actually start to do is we can start to analyze and look at the light that's being generated and passing through us. So if we take, for example, so imagine, there's an observer here, like so. So that's the person's eye. So what happens is if we take we take a star, for example, like the sun, and it's just sitting there, it's not moving. What happens is it's going to generate, or it's going to give off light. Okay, and then what we can do is we can pass that light through a spectra like this. So this, for example, is what it might look like when the star is not moving. And what you can see here is that you have this, again, we get this, we pass it through a prism and it splits up the light, and we get, we look at that and we see this particular type of spectrum here. Now, what happens then is, like, let's say the Earth or the Sun is moving forward in this direction, okay, or the observer, for example, is moving forward. What's going to happen then is that the light, the wavelengths of light are going to get bunched up, or if you like, the wavelengths of light here and here is going to get shorter. So as a result of that, if it gets shorter, what happens is these absorption spectra shift to the left. So you can see here, this is, let's say, it's not moving, so it's not moving, and this is where it's moving, if it's moving towards you. So what happens is the wavelengths kind of get bunched up and they become shorter, and as a result of this, it moves the spectra, it shifts to the left, and this is what's known as a blue shift. And this indicates that if you see a spectra, something like that, it indicates that this particular star is moving towards the observer, because the wavelengths get shorter. It's kind of like the Doppler effect. Now the opposite then happens. So what happens then, let's say, if this star starts to move, it's moving away in the opposite direction. Well, what's going to happen is the wavelengths are actually going to get longer. The wavelengths will get longer, and what will happen then is you will get this kind of setup here. So this is moving away. So you get what's known as a redshift. So what happens is the absorption, these absorption lines, they actually start to move to the right. So this is stationary. Okay, when the star is stationary, if the star is moving towards you, the lines start to punch up, and as a result, we get these absorption lines start to move to the left. If the star is moving away from you, what happens is these absorption lines start to move to the right. And we can actually, spectra can be used to figure out and look at the motion of stars like in this way as well. Now, another thing that can happen then as well is you can get what's known as rotational movement. So let's say if the star is moving, let's say in this direction. So it's rotating around like this. Well, what's going to happen is you're going to get the light coming off from the middle of the star. So for example, the middle light will come off from the middle of the star, it'll come off something like this. And then what will happen is the light then, if you like, the light from the top part of the star, from up here, it's going to be moving like this. So this top part is moving towards you, moving towards the person. So what's going to happen is with the top part, the wavelengths are going to be a little bit shorter than these longer wavelengths down here. So you're going to get this kind of a wavelength effect from the top part of the star where it's moving towards you. And then if you think the bottom part, this is actually moving away from you. So what's going to happen is you're actually going to get longer, even longer wavelengths down here. Similar to this, if it's moving away from you, you're going to get this redshift. So what happens then to the overall, let's say, spectra? You get something like this. So you get the same spectral lines, but the lines themselves are being spread in both directions, like so. So essentially what's happening is you're getting wider lines. So if you look at this in comparison to, so for example this, so you have the same lines, but they're much wider apart. So they are like so. So you get these big thicker lines. So what that indicates is that the particular star is rotating. So for example, it's rotating in this way. And again, depending on the light and which part of the star it's coming from, it can then be used to determine you know, what the star is actually doing, what way is it moving. And this is what's known as rotational movement, and it can be picked up using spectra. So that's like just some of the uses, for example, of spectrophotometry in relation to the study of stars. So we've looked at quite a few things here today, just in relation to this very interesting and fascinating topic. So we kind of looked at things like, you know, how we can take the starlight, break it down, and we can create and generate particular types of emission spectra, and then we can look at those emission spectra to look at the chemical makeup, like what we've seen here. We can then use that, we can take the starlight, for example, the light from the sun, and we can identify these individual absorption lines on a continuous spectrum from the light from the sun, for example, and we can pick out and identify these characteristic wavelengths that are being absorbed by the star, and we can determine like what the chemical makeup is of it. We can also then as well use, so for example, we can link in, let's say, the particular wavelength of light that a star is given off, and we can link that into its temperature using this, and we can then actually start to classify stars into different groups as well. And then we can start to look at the absorption spectra of these particular classes of stars. As they get cooler, you get more elements that are being formed, and the more elements that are being formed, the more lines that will actually show up in the absorption spectra. And this happens, why do you get these absorption spectra? Because you get white light that's coming from the sun, it's passing through this layer, or from stars as well, it's passing through this layer that's known as the photosphere, which you can think about as just like the atmosphere around a particular star. And just like we get here, this kind of setup, so this gas here is representing this photosphere. The light passes through, and depending on the elements that are present within the photosphere, particular wavelengths of light are absorbed. So we can use it the absorption spectrum or light to analyze those aspects of the stars. And then what we can do, like what we've talked about, we can look at the different density. So for example, if the photosphere is very dense, you're going to get this kind of a spectra being generated. If the photosphere is not as dense, you're going to get this kind of these fine lines being generated. And then finally, then we can start to look at what direction the star is moving. If it's moving towards you, the wavelengths will be tightly packed, and there'll be what's called a blue shift. So you get this kind of this blue shift here. So this is like, let's say, a spectrum with no movement. This is where the star is moving towards you. You can see the absorption lines are moving over to the left. The opposite happens if it's moving away. The wavelengths get longer, it's moving to the right. And then if it's rotating, what happens is the lines actually start to get thicker as well. So it's just a quick introduction and some of the interesting ways that spectrophotometry and the study of light and absorption spectra and splitting up light, how it can be used to analyze stars that are millions and millions of miles away in the depths of space. Okay, so hopefully you found that interesting, and thank you for your time.